Welcome to another tutor short provided by the Educational Support Services Department of Lehigh Carbon Community College in Snexville, Pennsylvania, which is just outside of Allentown. These videos review key learnings for the science courses provided here at L-Tri-C. And please remember that the Educational Support Services Department does provide walk-in tutoring 5 days a week. Today we will look at the unit of measure in chemistry called the mole, and how it relates to Avogadro's number and why it is so important when learning chemistry. Let's start by taking a look at the simple chemical formula you see before you. Sodium will combine with chlorine and will make sodium chloride, which is common table salt. By looking at this equation, you might assume that if you had 1 gram of sodium and you combined it with 1 gram of chlorine, that you would make 2 grams of sodium chloride. Conservation of mass, 1 plus 1, your sodium chloride would weigh 2. But this would be wrong. The chemical equation you see before you does not pertain directly to weights. It pertains to atoms. The formula really tells you 1 atom of sodium will react with 1 atom of chlorine to form 1 molecule of sodium chloride. And sodium and chlorine weigh different amounts. The atomic mass of sodium is about 23, and the units of atomic mass are AMU, atomic mass units. And chlorine is about 35 AMUs for each atom. So if you react these two particles together, two elements, you would make a sodium chloride molecule that would, added together here, weigh 58 AMUs, atomic mass units. Now, in a practical sense of day-to-day use, we don't go around picking up 1 atom and reacting it with another atom and trying to do that, say, on a bench or even in your kitchen when you're making something. And the AMU is a very, very tiny number, tiny mass, and obviously, an atom of sodium doesn't weigh very much. We're talking somewhere in the order of 10 to the minus 30 grams. So you can't really deal with these very, very small numbers. So early chemists, a few hundred years, I guess about 150 years ago or so, try to figure out a simple way to be able to deal with these chemical formulas with units that are more practical for us to use, for example, grams. So the unit they came up with, if you want to call the mole, is, if you remember, sodium was 23 AMUs. They said, well, what if we could come up with a way to make that AMU just change it to grams? So 23 grams of sodium. Chlorine was about 35 AMUs. What if we could get to 35 grams, and then added together you would form 58 grams of sodium chloride. And the way to get from AMU up to grams, if you remember, 23 was how much 1 atom of sodium weighed. They found that if you took 6.022 times 10 to the 23 sodium atoms, then it would weigh 23 grams. And because all atoms, molecules, are made up of the same atomic particles, protons, neutrons, and electrons, it turns out, very conveniently, that chlorine atom weighs 35 AMU. If you take 6.022 times 10 to the 23rd chlorine atoms, you'll find their weight to be 35 grams. And likewise, over here, if you just took 1 molecule sodium chloride, it would weigh 58 AMUs. But if you took 6.022 times 10 to the 23 of those molecules, they would weigh 58 grams. And so by using this number, which was called Avogadro's number, you can, by simply looking at the periodic table, looking at the atomic mass units of the individual atoms, if you took this many, you could just take that AMU value of mass and just make it equal to grams. And so a mole is essentially a count. If you have a mole of sodium chloride molecules, that means you have 6.022 times 1023 molecules of sodium chloride, and that mole will weigh, if you have that many molecules, will weigh 58 grams. So you'll often see the term 58 grams per mole is how much sodium chloride weighs. They'll call that the molar mass. 1 mole of sodium chloride weighs 58 grams. Same thing with chlorine. A mole of chlorine atoms weighs 35 grams. And a mole of sodium atoms will weigh 23 grams. So it makes a very convenient way to look at these values to essentially, if you wanted, let's take another example using this information. Let's say we wanted to make some sodium chloride in the lab. And very simply, if you want to look, let's say we wanted to make, let's say 2, so 58 times 2 is 116. If we wanted to make 116 grams of sodium chloride, how do we do it? How much sodium and how much chlorine do we need? Well, we know that sodium chloride, if we had 1 mole of sodium chloride, it would weigh 58 grams. But we want 116, and because I used the right number, essentially means we need 2 moles of or we're trying to make 2 moles of sodium chloride. It would take, to make 2 moles of sodium chloride, you'll see in a chemical equation, a big 2 here, we want to make 2 sodium chloride molecules, or moles, 2 sodium chloride. Then we're going to need 2 sodiums and 2 chlorines in order to make this compound. And so we need 2 moles of sodium. We know that 2 moles we need of sodium, and we know that there are 23 grams in 1 mole. So that means we need 46 grams of sodium in order to make this table salt. And since we need 2 moles of chlorine, and chlorine weighs 35 grams per mole, then we need 70 grams of chlorine. And if you add 70 grams of chlorine with 46 grams of sodium, you'll see the conservation of mass. We get 116 grams over here of sodium chloride. So it's using the chemical equation and this unit of measure, the mole, we can deal with everyday values or volumes and masses of atoms and molecules. If we wanted to make something in the lab, like we said here, we wanted to make about 116 grams of table salt, we would need 46 grams of sodium and 70 grams of chlorine in order to do that.